All right, guys, so this next video, we're going to talk about rotational kinetic energy. So if you remember in our previous chapter when we talked about energy, we talked about kinetic energy and potential energies, and we talked about gravitational potential energy and elastic potential energy when we have springs, right? The kinetic energy that we talked about then was for what's called translational motions, the motion, along a line or along the X, Y, Z axis. What we're going to talk about here is a different type of energy and a different type of motion. This is the kinetic energy due to the rotation of an object. So rotation is a motion, just like translation is. And as such, it has a kinetic energy associated with it. So when we think about the equation for this rotational kinetic energy, let's start off with what we know. So let's start with this ball, and we'll say we have a center of mass, and the center of mass has a certain velocity v. So we would say that it has a kinetic energy of 1/2 mv squared. And so we know this equation very, very well. We've used it a lot. But the ball itself is rotating as well. So say it's rotating that way, right? So the ball itself is rotating, and it has a certain kinetic energy due to the rotational motion. And what happens very often, as you know, with rotationals, we make these analogies between the translational stuff that we're more familiar with and the rotational motion. So if you remember in these types of equations, when we have mass, what we replace that with in the rotational analog to that is the moment of inertia. So the rotational kinetic energy would be 1/2 the moment of inertia, and instead of velocity, we use angular velocity, omega squared. So this is the equation for the rotational kinetic energy, where I is our moment of inertia, and then this omega is the angular velocity in radians per second. Okay, so very similar looking equations, but this moment of inertia, the fact that we're using moment of inertia and not just the mass, has some interesting effects. Namely, as you know, the moment of inertia is different for different shaped objects. So if we had, say, a disk, it would have a moment of inertia that calculated as 1/2 mr squared. Whereas if we have a hoop, it would be just mr squared. So even though they have the same mass, they could have, and the same radius even, they can have different moments of inertia. And therefore, if their moments of inertia are different, the rotational kinetic energies will be different as well. So when we calculate this, we do have to consider, all these equations for the rotational inertias of the different objects. If we have a ball, it's going to be 2/5. If we have a hollowed ball, it's going to be 2/3 mr squared. If we have hoops or tires or whatever, all of these can have the same angular velocity, the same mass, and yet different rotational kinetic energies because they have different moments of inertia. Now, a very classic example of how this gets displayed is if we have, say, a hoop, and then we have, a sphere, or maybe some other object going down at the same time. So both of these, this is a ramp. Okay, so we're going to let these roll down the ramp, and they both start at the same height, h. And so they're going to start with the same gravitational potential energy, and then we're going to let them roll down. And at the bottom, when we think of what's happened, all this gravitational potential energy will be transferred into kinetic energy at the bottom, because we'll put a reference point at the bottom of the ramp. But now, instead of just saying it's equal to the translational kinetic energy, it's going to be equal to the translational kinetic energy of its center of mass, so we're going to pay attention to the center of mass there, and its velocity, plus the kinetic energy of the rotation, okay? And so we'll have an equation, mgh is equal to 1/2 mv squared plus 1/2 I r squared. And so this total potential energy we start with is going to be split up between the translational kinetic energy and the rotational kinetic energy. And it turns out that the higher the rotational kinetic energy is, so mainly the higher this moment of inertia, okay, possibly the, sorry, I put r squared, omega squared. The higher this moment of inertia, the lower the velocity of the center of mass is. And it's actually going to take longer for it to go down. It's going to be moving more slowly if it has a high moment of inertia comparative, it has a lower moment of inertia. So this is a very classic conceptual problem. And this is what we looked at in our activity during class, is the effect of moment of inertia on the velocity of the center of mass of the object as it rolls down the ramp. And so we'll consider other samples, other systems where this comes into play as well during class. So make sure you get these equations down, especially the equation for the rotational kinetic energy. And if you have any questions, please let me know.